Acids and bases play important role in organic chemistry, and in this video we will review basic concepts related to acids and bases. That will be Bronsted-Lowry definition of acids and bases, what is acid-base equilibrium, and Lewis definition of acids and bases. Two definitions of acids and bases that are commonly used in organic chemistry are Bronsted-Lowry definition and Lewis definition. Of the two, Bronsted-Lowry is more commonly used, although Lewis concept also has very important uses. According to Bronsted and Lowry, an acid is proton donor and base is proton acceptor. An acid-base reaction is proton transfer reaction. It's transfer of proton from acid to base to give conjugate acid and conjugate base pair. So any acid-base reaction actually results in formation of new acid-base pair. So an acid upon loss of a proton gives rise to conjugate base, and a base upon gaining of proton gives rise to conjugate acid. Here is an example. So hydrogen chloride acts as an acid in reaction with water, which acts as a base. Proton is transferred from hydrogen chloride to water to give hydronium ion, or conjugate acid of water, and chloride anion, or conjugate base of hydrochloric acid. In another example, molecule of water acts as an acid and reacts with ammonia, which acts as a base. Proton is transferred from water to ammonia to give ammonium cation, conjugate acid of ammonia, and hydroxide anion, conjugate base of water. From these two examples, you can see that in one case water acted as a base and in another as acid. So a particular compound is not classified as acid or a base on its own, but rather in a reaction, depending on whether it's proton donor or proton acceptor, we classify it as acid or base. So in general, we are looking for an acid-base pair that reacts, not to classify a particular compound as acid or a base. Here are some organic chemistry examples. First, acid is formic acid, and it reacts with water as a base to give formate anion, conjugate base, and hydronium ion, conjugate acid. In the next row, we have a molecule of acetone that acts as an acid and is deprotonated by sodium hydride, very strong base. So we get enolate anion, conjugate base, and in this case molecule of hydrogen is evolved, which strictly speaking is conjugate acid. This is something we'll cover quite a bit in second semester. And the last example is reaction of hydrogen iodide with an ether. So hydrogen iodide acts as an acid. In this case, dimethyl ether is a base. We get oxonium ion as conjugate acid and iodide anion as conjugate base. Bronsted-Lowry definition of acids and bases gives rise to important concepts of pKa and pH. So an acid-base reaction is equilibrium reaction. An acid reacts with a base to give conjugate acid-base pair. Conjugate acid and conjugate base are acid-base pair, and so proton can be transferred from conjugate acid to conjugate base in a reverse reaction to give acid-base pair. Since this is an equilibrium reaction, we can define equilibrium constant for such reaction. And we can see that this equilibrium constant involves concentrations of conjugate acid and conjugate base, acid, and then there is acid and water that acts as a base. But typically, such reactions are carried out in dilute solutions, which means that within margin of error, concentration of water is constant. Simply we round concentrations to a certain number, and within rounding error, typically concentration of water is constant, which means that we can incorporate concentration of water into the equilibrium constant and define new equilibrium constant, acidity constant. So equilibrium constant multiplied by concentration of water is equilibrium constant. And so equilibrium constant is concentration of conjugate acid multiplied by concentration of conjugate base divided by concentration of the starting acid. The acidity constant tells us how strong acid is. If acidity constant is large, that means equilibrium is to the right. and acid is efficient proton donor, which means it's very strong acid. On the other hand, if equilibrium constant is small, then equilibrium is to the left. Acid doesn't have very high tendency to donate proton, so equilibrium is to the left. These values for Ka vary quite a lot. They could be certain number times 10 to, let's say, negative 16, negative 28 for weak acid, or it could be, let's say, 5 times 10 to 7th, or 6 times 10 to 9th, or something like that. So typically, they involve exponents. And given that there is such a large range and numbers involve exponents, Ka is not very convenient to use. For that reason, we define new quantity, and that's pKa. P literally stands for potential of Ka, but we can just call it pKa. And that's negative logarithm of Ka. Since this is negative logarithm, relationship to Ka is inverse. So while large Ka meant strong acid and small Ka weak acid, here large value for pKa means weak acid, while small value for pKa means strong acid. And pKa could be negative. So very strong acids would have negative pKa's, like -7, -9. Those would be among the strongest acids. While acids that have Ka 6, 7, 10, those are weak acids. And finally, you need to be familiar with pH, and pH tells us about the acidity of the solution. What is the acidity of the aqueous solution? pH is negative logarithm of concentration of hydronium ions. So pH of 7 is neutral solution, above 7 basic, and below 7 solution is acidic. In organic chemistry and related fields such as biochemistry, it is very important to know the position of the acid-base equilibrium, to know whether a particular species is in the form of acid or conjugate base or its conjugate acid, because that's very important to know the properties that that species will exhibit and also properties of the solution, and to explain reactivity and reaction mechanism. So it is very important to know the position of the acid-base equilibrium. And so here we have a couple of examples. We have example of reaction of acetic acid with ammonia. And that's, acetic acid obviously acts as an acid, ammonia as a base. Conjugate base is acetate anion, and ammonium cation is conjugate acid. So the question is, where is equilibrium going to be? As a general rule, for any acid-base reaction, strong acid and strong base react to give weak acid-base pair. So that is a spontaneous process. Spontaneous process means reaction of strong acid with strong base to give weak acid and weak base. You can think, as an example, reaction of hydrogen chloride with sodium hydroxide. That reaction would result in formation of sodium chloride and water. So that's typical general chemistry reaction, reaction of acid and base to give what we call salt and water. But really, according to Bronsted-Lowry definition, that would be conjugate acid, conjugate base. So in this case, we have strong acid, hydrogen chloride, and strong base, sodium hydroxide, that react to give a weak base, actually chloride and ion. Sodium, strictly speaking, is a spectator ion, and water, which would be weak acid. So strong acid and strong base react to give weak acid and weak base. Opposite reaction, reaction of sodium chloride with water to give hydrogen chloride and sodium hydroxide, is not going to happen spontaneously. And so if you remember that, particularly that example, then you will hopefully remember always that what is a spontaneous process. Strong acid and strong base react to give weak acid and weak base. But to be able to predict then position of the equilibrium, you need to know both strength of acid and base and then compare them. And sometimes you may wonder, what if in one case we have on one side strong acid and on the other side strong base, and then where is the equilibrium? Actually, the situation is much less complex than that. All you need to do is look at the acid strength and simplify that rule in stating that equilibrium will be at the position of weak acid. In other words, that reaction will proceed in such a way that strong acid gives rise to weak acid. In this case, we have acetic acid, pKa 4.76, and on the right we have ammonium cation, acid with pKa of 9.4. As I just explained, lower value for pKa means stronger acid, which means acetic acid is stronger acid. So that's a strong acid, ammonium cation weak acid, therefore equilibrium will be to the right. And so at equilibrium, when this reaction is carried out, at equilibrium we are going to have predominantly acetate anion and ammonium cation. In the second example, we have example of ethanol reacting with methylamine. Ethanol has pKa of 15.9, and then products are ethoxide anion and methylammonium cation. Now pKa values are 15.9 for ethanol, so pretty weak acid, and 10.7 for methylammonium cation. That's weak acid, but much stronger, considerably stronger compared to ethanol. Keep in mind this is logarithmic scale, which means that in this case equilibrium is to the left. So if we mix up ethanol and methylamine, extent of reaction is going to be very low. They will mainly remain in this form as mixture of ethanol and methylamine. We can determine, so this was qualitative determination of position of the acid-base equilibrium. We can determine position of the acid-base equilibrium quantitatively by calculating equilibrium constant for the particular process. And equilibrium constant is Ka of the reactant acid, that means one on the left side of the equation, divided by Ka of the product acid, conjugate acid, one on the right side of the equation. Whether an acid in aqueous solution will be in protonated or deprotonated form depends on the pKa of that acid and pH of solution. Quantitative relationship is given by Henderson-Hasselbalch equation. That equation states that pKa of the acid equals pH of the solution plus logarithm of the concentration of protonated acid divided by concentration of deprotonated acid. From this equation it follows that if pKa equals pH, then logarithm of HA over A minus equals 0, and that means logarithm of 0 is 1, HA over A minus is 1, or two concentrations are equal. So when pKa equals pH, it means that two concentrations are equal. Concentrations of protonated and deprotonated acid are equal. So as pH of the solution increases, concentration of protonated acid decreases and deprotonated increases. And conversely, if pH of the solution decreases, concentration of protonated acid increases and deprotonated increases. But at any point we have a mixture. We are mainly concerned with which species is predominant. So are the two present in about equal amounts, or does one predominate? And in general, it's only a rough estimate, but we will assume that if one species is present in 90% amount or more, then that's the only species in the solution. Obviously, it's a rough estimate, and we understand that both are still present in the solution. So we can use Henderson-Hasselbalch equation to estimate relationship between pH and pKa and when each species will be present in the solution. So we can tell that two species, protonated and deprotonated, will be present in about equal amount if pH of the solution is in the range of pKa plus minus 1. Now, if pH equals pKa minus 1, so if pH of the solution is a pKa minus 1 or lower, then acid exists predominantly in the protonated form. And if pH of the solution is pKa plus 1 or higher, then acid exists predominantly in deprotonated form. We can apply that on a couple of examples. First example is carboxylic acid, just generic carboxylic acid in aqueous solution. Typical carboxylic acid has pKa value of about 4.5. So that means that if pH of the solution is in the range of between 3.5 and 5.5, there will be a mixture of about equal amounts of protonated and deprotonated acid. Below 3.5, carboxylic acid will remain in protonated form, and above 5.5, mainly in deprotonated form. In the second example of an amine, typical amine has pK value of about 10, or protonated amine has pK value of about 10. So if the pH of the solution is in the range of between 9 and 11, then two species amine and ammonium salt, protonated amine, will be present in about equal amount. Below 9, amine will be mainly in protonated form, in form of ammonium cation, and about 11 mainly in the protonated form, in form of amine. Another definition of acids and bases that is commonly used in organic chemistry is Lewis acid base definition. The Bronsted-Lowry definition is very useful. It doesn't cover all the cases. So there are quite a few limitations. When we consider a reaction like this, reaction of ammonia with boron trifluoride, the two molecules react to form new molecule of salt. But there is no proton transfer, so it cannot be classified as acid-base reaction using Bronsted-Lowry definition. But we can classify it as acid-base reaction using Lewis acid-base definition. That definition is obviously more general compared to Bronsted-Lowry definition. And so, according to Lewis definition, Lewis acid is an electron pair acceptor, and base is electron pair donor. So Lewis acid and bases are defined through electron pair. And so, according to Lewis, proton itself is an acid because it's electron pair acceptor. So that takes care, according to Lewis, of Bronsted-Lowry definition. It's very easy to remember which is which because acid is electron pair acceptor, and both word acid and acceptor start with AC. So here are some additional examples of Lewis acid-base reactions. So Lewis base, by being electron pair donor, must have at least one free electron pair. And Lewis acid, by being electron pair acceptor, must have empty orbital to which this electron pair can be donated. So Lewis acid, by definition, must have a free electron pair. So here we have an example of reaction of boron trifluoride with dimethyl ether to give corresponding salt. In another example on the right, aluminum trichloride is another example of Lewis acid, and reaction with trimethylamine, Lewis base, again gives a salt. One other important class of Lewis acids are carbocations. They are common reaction intermediates, and of course they have an empty orbital, so they can act as Lewis acids. And in fact, this is usually how they react. They are formed as short-lived intermediates in organic reaction, and typically in the following step they will react to Lewis base, which we usually call, in that case, a nucleophile, to give the next intermediate or final product of the reaction. Now, Lewis base theory is used quite a lot in organic chemistry, but we have to distinguish between Lewis acid-base definition and Bronsted-Lowry definition. So, if we simply call species acids and bases without specifying which definition we are using, it means that we are using Bronsted-Lowry theory, and we are talking about proton transfer as acid-base reaction. If we want to refer to Lewis acid and base, then we have to specify. We have to call those species Lewis acids and Lewis bases to indicate that we are using Lewis acid-base definition. This completes introduction into acids and bases, and next we are going to look at specific examples of organic acids and bases.